Hello and welcome to another review session for your Calculus 3208 final exam presented by CDLI. And we're going to start into a sort of a new subtopic of our applications of differentiation unit. And our subtopic today that we're going to talk about is the first bit of our lead up to being able to sketch graphs of all different kinds of functions using calculus. And so one of the tools that we need is what we're going to develop today, and that is finding out where a function is increasing and decreasing and where it switches back and forth between those two things. So we're going to talk about something called critical values. So critical values are important stuff. Critical values are places on a graph where we change from increasing to decreasing. That's basically what that is. And we're going to find intervals of increase and decrease based on what we see from our critical values. Okay, so let's get started. So the concepts of increasing and decreasing behavior on any given interval, if the first derivative of a function is positive, we know that that means that the tangent lines have positive slopes, and therefore the function f of x is increasing. We saw that before, but we're just going to review these concepts real quickly. And we know that if the first derivative is negative, it means the tangents have negative slopes everywhere on that interval. And so therefore, f of x would have to be a decreasing function as long as that's true. And if the first derivative is equal to 0, then the tangents would be horizontal, which typically means at that point we either get a maximum value, a minimum value, or something called an inflection. But don't worry too much about all this stuff for this section. You should know about that stuff anyway by this point in your course. But that stuff right now we'll get into more detail later. So let's just start off with what we're really interested in here. We're going to talk about critical values and what they mean. So it is a change in behavior of a function, okay? And really, there's two different ways that they come about, and this is a common misconception. A lot of times folks will think you only get critical values at a vertex, which is a maximum or a minimum point. But that's not really the case. And a lot of times folks will say that you get your critical values by letting your derivative equal to 0 and then solving for the x or the variable that you're using, which is one way to get them, but it's not the only way. So we don't want to overlook the detail here. So if we look at this first graph that we have here, looks like it's an even-powered polynomial probably. And I want you to look at that point right there. And at that point, we're going to have an x-coordinate of a, as it says up here. And it says right there, f prime of a equals 0. And that's that situation that we mentioned on our last slide there. That's what happens if we're dealing with a function when we have a horizontal tangent. And that's one way that we get a critical value, is that horizontal tangent making our first derivative equal to 0. And that's the standard way. That's usually the kind of thing that we end up coming up with. But it's not the only one, so we have to be careful. We could also have values where the derivative f prime of a is undefined. And if the derivative is undefined, then we can also change behavior from increasing to decreasing. We don't necessarily have to, but technically to be a critical value, it's if we can change behavior at that point, then it's going to be critical. So let's see. In this next one, we do have a maximum value here, but we certainly don't have a slope of 0. So there's no tangent line at x equals a at all for this particular graph. That's a corner point, sometimes called a cusp point. But for that particular function, we can see that this would, in fact, x equals a, be a critical value for that one. So we do have a critical value there, even though we don't have this horizontal tangent business happening. And if we look over at the far right, that last graph that we have there, there's this discontinuity, a jump discontinuity, in fact, happening at x equals a. So the graph is increasing before and it's increasing after, so that didn't change, but it does bring you to mind that if a graph is discontinuous at a point, then its derivative won't exist. So the derivative is actually undefined. And we have to be careful about that, because as long as the derivative is undefined, we have the potential for this to change. This could very easily have been a graph that went this way afterward, and then we would have been increasing before the point and decreasing after. So we don't know if we don't have the graph right in front of us, so we have to check out those values. Also, we often see that there's a change in increasing and decreasing behavior for a function on either side of an asymptote, and that would also be a place where the derivative is undefined. So what we have to keep in mind is that we get critical values whenever f prime a is equal to 0, or whenever it's also, like over here, if it's undefined. Those are the big things. So hammering that point, hopefully getting it through to make sure that we don't overlook that. All right, so let's look at some examples. It says determine the intervals of increase and decrease for this function. So the way that we do that is we first identify the critical values, because they're the places where we can change from being increasing to decreasing or vice versa. So we have to identify the critical values, and then we're going to use something called a sign graph to help us figure out what the function is doing on all the intervals in between the critical values. And that's the basic theory of it. So in order to do that, we only need our first derivative, so let's get that one, f prime of x here. So for my first term, 1/3 of x cubed, using the power rule, I get x squared, because 3 times a third is 1. And then for subtract x squared, I'm going to get minus 2x. And for the negative 15x, I get a derivative of minus 15. And of course, the derivative of 7 will be 0. So what we've got here is a polynomial function. That is really, you're fortunate if you get one of these questions and you're dealing with a polynomial, because polynomials don't have discontinuities in them unless we define them to have them for some particular weird reason. And polynomials are everywhere differentiable. So that makes it way nicer, unless of course we have a point with a vertical tangent, but that doesn't happen very often and won't happen to a typical polynomial. So what we see here is that we have x squared minus 2x minus 15. There's no way that function's ever going to be undefined unless we have some weirdness, and we don't have that. So we're just going to let it equal 0 in this case, and we can get off easy by finding out what are the zeros of this function. So I've got x minus 5 times x plus 3. So I'm going to get 2 critical values, and my 2 critical values are going to be at x equals negative 3 and positive 5. But that's not what our overall goal was here. It was to determine the intervals of increase and decrease for the function. So what we do to deal with that, and there's lots of different ways that folks write these things out, but the way that I typically do it is I use a number line sign diagram. So we just draw a number line, and on our number line we're going to plot our critical values as just a couple of points or values for x. So I'll put 1 over here for negative 3, and I can put 1 way over here somewhere for positive 5. And you can label your number line in a lot more detail than that, but for the sake of what we're doing here, it's not really necessary. So I'm going to say x equals negative 3 right there, and x equals positive 5 right here. And there's a number line to represent the domain of this function. Okay, so I'm going to put a little circle around each of those to indicate that neither one of them is going to be included as a point where the function is increasing or decreasing, because remember the derivative was actually 0 there. So we have a horizontal tangent with neither increasing nor decreasing. Then what I do is above the line I put an f prime to indicate that I want to look at what the derivative is doing. And then below the line I put a little f down here, and what that'll do is it'll help me determine how the function is behaving based on what I figure out about the derivative. So I'm going to take my derivative and I'm going to test all the intervals that I see here, all 3 of them, and decide how my function is behaving. So let's find f prime. First place to check would probably be negative 4, just to the left of negative 3, and that'll tell us about that first interval. So we'll have negative 4 squared minus 2 times negative 4 minus 15. So what that gives us is 16 and 8 minus 15. So it's 24 minus 15, or positive 9. Positive 9 tells me the first derivative is positive. So on that interval, the first derivative will always be positive. There's no place for it to change. There's no critical values in that interval. So not only is it positive, but that tells us that the slopes of the tangent lines are positive. So our original function f is always moving upward or increasing on that interval. Let's try 0. 0 is smack dab in the middle of our next interval. So we have 0 squared minus 2 by 0 minus 15, which gives us a negative 15. That's a negative number. So in this interval, our first derivative is always going to be negative, which tells us slopes of the tangents are negative. The graph of f is on its way down as we go left to right, so it's decreasing. And the last thing we want to do is pick one more test point. So let's go, I don't know, x equals 6. So we've got 6 squared minus 2 by 6 minus 15. I'm going to watch my minuses. So I've got 36 minus 12 minus 15. Putting all that together, I've got 36 subtract 27, which gives me a value of 9 again. So if that's positive, and we can see that the function will be increasing out there. So to write a solution for this, they want to know the intervals of increase and decrease. And I'd usually write that in interval notation. So I'd say I'm increasing on an interval, and I'm going to be decreasing on an interval. And for increase, I've got all the values of x from negative infinity up to negative 3 to start with. So we're going to go from minus infinity up to minus 3. And then we're going to join that up with, or have a union with, the set that starts at 5 and goes on to positive infinity. No square brackets here because none of those points are allowed to be included. Okay, and so I've got those two joined intervals, mutually exclusive, but thrown together for the purposes here. And our function is going to be decreasing on an interval that starts at -3, goes up to +5, doesn't include either endpoint. Okay, so that's how we find intervals of increase and decrease for a function. Polynomials are nice to do that with. But not all of our functions are polynomials, so we've got to do the same thing now for a rational function. So this is where we really got to be on our guard. Keep your guard up on this one, folks. Here we go. So this says x cubed over x squared minus 1. So let's get a derivative for that first. F prime. Okay, quotient rule. Derivative of the numerator will be 3x squared multiplied by my denominator x squared minus 1. And then I have to subtract the derivative of the denominator, which is 2x, multiplied by my numerator, which is x cubed. And then all of that is going to have to be divided by x squared minus 1, all squared. So in my numerator, this simplifies to give me 3x to the power 4, minus 3x squared, and then minus 2x to the power 4, all over x squared minus 1 squared. So simplifying my numerator a little bit further, I've got x to the power 4 minus 3x squared, all divided by x squared minus 1 squared. So I have to identify my critical values now. So there's going to be two places where we can get critical values for this stuff. So the first place is when that derivative is equal to 0. So we'll look for zeros of the derivative first. So zeros of my derivative will happen at x to the power 4 minus 3x squared over this stuff being equal to 0. And if I were a betting person, which I'm not, but if I were, I would say that this stuff down here is never going to make that fraction equal 0. So I'm only going to worry about the numerator being equal to 0. And that can factor. So I've got a common factor of x squared, leaving me with x squared minus 3. So I'm going to get roots at x equals 0, a double root for this one. And for the other one, I'm going to get x equals plus or minus the square root of 3. So from my numerator alone, I've got 3 critical values. And then I've got to look at places where this function could be undefined, or sorry, where the derivative could be undefined, excuse me. So what are the undefined values of my derivative? And the undefined values of the derivative here are going to be any place where my denominator is equal to 0, because that's going to be the only thing that restricts the domain of this. So if that denominator is going to be equal to 0, it would mean that x squared minus 1 would have to be 0. And if that's going to happen, x would have to be plus or minus 1. Okay, so I've got 5 critical values. Wow, so there's a lot of work to this. So we've got critical values at x equals negative root 3, x equals -1, x equals 0, x equals positive 1, and x equals the square root of 3. So lots of different places to check out. 5 critical values means I've got to test 6 intervals. Hopefully our arithmetic will go quick with that. Okay, so what I'm going to do is I'm just going to erase a few things here. So if you're scribbling things down in a frantic hurry, make sure that you copy them out fast. I'm going to just make a note of what my derivative was, though, because I'm going to need that to do my derivative tests that are coming down the pipe. So I'm going to say f prime of x. We had that one already. That's x to the power of 4 minus 3x squared all over x squared minus 1 squared. Okay. So I'll make a note of that, and then I'm going to delete all the rest of this stuff out of our way now so we can do our derivative testing. All right, so what we'll do now is we'll draw a number line, and on that number line, we're going to have to include all of those critical values and some numbers that'll make it look nice for us. So the furthest left and right we get on here will be minus root 3 and positive root 3 over here. And then we're going to be at -1 and 0 and positive 1. Note that this is not drawn to scale, but we don't really care. We're just doing it to get us an idea of what's happening. So we'll look at the behavior of f on all of those places, f prime, and see what that tells us about f, and that will tell us our increase and decrease. All right, so for f prime, I have to evaluate at all of these different places to see whether we're positive or negative. if you look at the derivative that we had, notice that the denominator we're dealing with here is actually squared. So if we're dealing with a squared denominator, that will never be a negative. So I'm not going to worry too much about that. All I'm going to think about when I'm testing my derivative is that I always have a positive denominator, and I'm just going to want to figure out whether or not my numerator is going to be positive or negative. Now typically, for a function like this, and with some complicated numbers, you'd probably take a calculator and work that out. But, and if this was probably a question like you get on your calculus placement test, the CPT that's coming up for a lot of you later on this year, you don't really have to, they probably won't give you stuff that requires a calculator to work out anyway, so won't be a big deal. But if we want to use one for today, that's okay for this business. So let's put our circles on our roots here at all of these special places that we have come to know and love, and then we'll evaluate just the numerator, which was x to the power of 4, and we're going to subtract 3x squared, so you can hear me talking to myself as I punch these buttons in my calculator. Okay, so all I have to do now is ask my calculator to figure out the value of that bit at all of those important places. Okay, so we're going to ask our calculator to evaluate f of, and let's make a list of some intervals or some points in the intervals that we can use as test points to help us out. So in the first interval that we see there, a good test point might be at -2, because I know that the square root 3 is not quite -2, because square root 4 would be 2, so negative square root 3 is out the other side. So -2 would be good, and then we'll say -1.5 in our second interval, and then -0.5, and then we'll evaluate at 0.5, and at 1.5, and at 2. And if I can determine whether I'm positive or negative at all of those places, then that'll be all the information I need for my intervals of increase and decrease. Okay, so let's get down to that. I'm going to ask my magic calculator to do the magic calculation for me now. So we got -2 and -1.5. I'm getting them all punched in, and now my magic calculator is going to give me the answer here. Aha, and there it is. Now I have it. So that tells me that we're positive, and we're negative, and then negative again. Wow, look at that. Okay, and then negative again here, and then we are negative again there, and then on the last interval, we're going to be positive again. So all of those things divided by a positive will stay true to their word. So we're going to have a positive, negative, 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 and positive. So notice that we didn't have to change sign at all the critical values, but it sometimes works out like that. Okie dokie. So if we're going to write out our intervals of increase and decrease here, we're going to be increasing on, sorry about that, increasing only on the very two far ends. So when x is an element of -infinity up to -square root 3, and then from square root 3 and beyond. And for our intervals of decrease, this is a bit of a funny monkey. Really, we're going to have to put this together, because although it looks like it's decreasing all the way through here, at the actual critical values it's not. At those points we can't count them. So what we have to do is just sort of write them all out and just sort of skip over those points. So we're going to go negative root 3 up to -1, and then we're going to have to restart at -1 up to 0, and then restart again at 0 and go up to +1. And then we're going to have to restart one last time and go from +1 up to positive root 3. And so there's all the places where we're decreasing. Okay, so that's a neat one. A lot of detail in that question. Okay, so here's the next question. What are the critical values for this function? And it's a multiple choice question, so this is a test type thing, and we've been given 3 options. So if we're going to find critical values, remember we need to get the derivative first. So f prime of x here is going to be the derivative of my numerator, which is 1 multiplied by my denominator. I'm using quotient rule, of course. Subtract the derivative of the denominator multiplied by the numerator, all over the denominator squared, so 1 minus x squared squared. squared. That sounds funny. So 1 minus x squared, and then we're going to have plus 2x squared all over 1 minus x squared and squared again. So that will give us 1 plus x squared in my numerator, and then in the denominator I have 1 minus x squared squared again. So remember, to get critical values, and we're just going to do this one by inspection because it's quicker, what I need to get are all the roots of the numerator and the roots of the denominator for a rational function, because the roots of the numerator will be zeros and the roots of the denominator will tell us where the derivative is undefined. There are no roots of this numerator. If I tried to solve that, I'd get x squared equals -1, and we know that we can't take the square root of -1 if we want to get a real number. So that one's no good for us. So it's only the stuff in the denominator. So we're going to get, in this case, throw away the outside square, and I have 1 minus x squared equals 0. So that factors as 1 minus x and 1 plus x. And so x could be plus or minus 1. So those are the critical values we'd have to investigate. And it looks to me like this is the answer. They tried to trick us with just one or the other. And then to say that there are none, I would say the motivation behind that, what we call distractor, was for those that are just looking at where it's got to be equal to 0, not where it's undefined. Okay? So those are some interesting questions. The last one was pretty quick. The two before that weren't so quick, but it's all the same kind of stuff we need to do. So here's a question for you. It says determine the critical values as well as the intervals of increase and decrease for the function. Aha, so when it's your turn, I make you do all the stuff. Just, if you can't see this very clearly right here, this says 12x to the power of 2/3. Not that my handwriting is much better. Minus 4x. So if you can't see that, that's a little bit of clarification for you. Sometimes these things don't come out too clearly. All right, so have a crack at that one, and I'll show you the solution now. So here's the solution, done in all of its gory detail with all the information that you need. So check that out, make sure you got it correct, and then we'll run through a quick breakdown of all the things that we looked at here today. So we saw critical values. There are any points where the derivative is 0 or undefined. And they may turn out to be vertices or local extreme points, or they could be other points where the derivative changes sign. So remember, they could be asymptotes or cusp points, all kinds of different things. And we find intervals of increase and decrease by finding all the critical values and then testing the intervals in between with the first derivative. Hope that helps. Happy studying. Ace your final exams.